MuniHac 2024, we are pleased to welcome Hécate. Hécate is a member of the Haskell community known for leading community projects related to documentation, cryptography, and generally making the life of Haskellers easier. They are a former member of the Haskell Foundation board and work as a backend developer in Haskell. And Hécate likes to spend time to foster an inclusive and wholesome community. And today's talk is about effect systems in practice.
Thank you very much. Can everyone hear me? Fantastic. People at the back, the slides are readable? All right. Excellent, thank you very much. So, my name is Hécate. I am indeed a software engineer and PM at Scrive. We're a Swedish company that does online contract signature with the backend in Haskell for 10 years or so. I am now helping a hand at the Haskell Foundation after having been a board member, and I do trade unionism at Solidaire Informatique, which is a French trade union. And today's accessory for this talk is going to be the mighty leak. So, thank you very much. You may follow this presentation on your phone or computer with this QR code if you want to snap it. I'll take maybe 5 seconds for you to take your phones. All right, maybe 7 seconds. All right. So, I'm going to talk about, first of all, what this talk is not about. It's very important to manage your expectations. Then we're going to talk about the need for tracking side effects and how IO does it. Then we're going to approach the topic of semantic effect tracking. And then we will talk about effect systems, their implementations and their tragedies. And we will then conclude on introducing the library Effectful, which has been developed at my company for the purpose of tracking effects in a large backend application. So this talk is not about the theoretical implications of algebraic effects, of or their deep implementation techniques like delimited continuations or such keywords. I invite you to check out the work of Alexis King and Ning Xie. They're much more qualified than me to talk about them, and they have published on the topic. So let's start with this. Some people know what that is. That is the documentation for the Java platform, and this is the equals method for the URL object. So how does one compare two URL objects? Well, they can do it in a variety of ways, but how Java decided to do it is to do a network resolution on the domain name. So if you have a program that has to compare two URLs at some point, and you're saying to yourself, oh, well, it's a bit slow, what is it blocking? It's because your program is doing I/O operations. It's because it's doing network resolution at the worst possible place. So, yes, incredible. So a bunch of clowns, as the emoji says. So I'm going to start with a couple of terminology points. Determinism. What is determinism? Well, it's a property of a deterministic expression of function. It's the idea that the output of an expression of a function stays the same if its input is the same. Same input, same output, all the time. Referential transparency is a property that says that you can replace a call to a function with its result in a safe and predictable manner. For example, if we are going to go back to our equals method here, can you safely replace every call to this method with its implementation? Perhaps not, perhaps yes. It's very difficult to say, and thus it's a very bad function. So side effects. What's the matter with side effects? The idea is that we don't want any alteration of the world outside in a way that matters to us. So do we want our functions to perform network resolution in our back or to launch missile strikes? No. Register allocation, however, is fairly essential. Meanwhile, in an eternal war alternative reality, based on launching missiles, we do not allocate registers willy-nilly. But here, this is our reality. So we allocate registers, and we do not launch missiles when we can avoid it. Side effects. So side effects, it's a concept that's pretty arbitrary, actually, because not every language has the same definition. So this is an extract from the Coca programming languages documentation that says that in the many effects that Coca has, exception and divergence, the combination is called pure, because this corresponds to the Haskell notion of purity. So in Haskell, what we call pure is actually an expression or function that can throw an exception or diverge, so never return. Now, does that mean that I/O is complete bullshit? No, because we needed an analytical framework to understand and anticipate the results of programs, and I/O was the option that was retained at the time to model those programs. But indeed, it is very contextual. The sequentiality of computations. So the idea is that when we implement a programming language based on the pure lambda calculus, and indeed based on mathematical expressions, the order in which operations are pre-evaluated for their results to be consumed does not matter. If you have two members of an expressions, they will be in Haskell evaluated based on their need. Do we need this member of this equation first or second? Well, this will determine when it's evaluated. So it's pretty much up to the runtime system to perform the evaluation of expressions. And indeed, when you do not interact with the outside world, life in plastic is indeed fantastic. But, there's always a but, how about computations that depend on each other? And in fact, how about computations that depend on the outside world? Then you need to enforce this term, sequentiality. You need to enforce that things happen in a fixed order. So, this is why we've invented monads to perform things in a fixed order. That's what monads are for. And also for writing tutorials. It's a bit of a circular dependency. I'm going to take a quick moment to remind the public of what function signature looks like. We've got a function. We've got two columns and an A. A is a variable. Here we've got a type called IO that has also an A. We call it higher order. You can just think of it as a container type. And at the bottom, we have a constraint on the left side of a fat arrow, which means that this A is constrained by this constraint that we have here. So we do not know much about this A, except that it has to fulfill the constraints on the left. So, semantic side effect tracking. As you can see, I've named these functions. I've given them names which are descriptive. I could have named them with the letters of the alphabet. So, but here I've named them trace because it's a function that traces a computation. Fetch from cache, it's a function that fetches a value from a cache, from Redis, for example, or a little database. Logging operation called log. If you want to fetch something from the database, you're going to call the function fetch from DB, and to throw an error, you're going to call the function throw error. So the names are quite essential because the type signatures don't say much about what they're actually doing. So you truly need an ambiguous, extremely specific name to have a good idea of what's going on. But they could be, in fact, doing anything. And that is a problem. The functions that you think are only doing read operations could be also doing write operations. Maybe a very simple example is when you go on someone's LinkedIn profile, you view this page, and in your mind you view a page, but this person is also informed that you view that page. So a write operation has been going on at some point in the backend to inform this person that you've been viewing their page. So sending a get query to the server has some side effects. And indeed, when we put all these functions together, we've got the tracing of the computation at the top level. We fetch from the cache. If there is nothing from the cache, we fetch from the database. We log our statements all across. And if not, if there is still nothing, we throw an error with not found. So putting every type of outside interaction into the I/O box is semantic opacity. This leads us into a mental framework, actually, of pure versus impure, good versus evil, safe versus unsafe, which is not only wrong, but also steers us in the wrong direction for thinking about systems. Let's clarify things a bit. Here, my trace function has also a constraint on this type variable ES with the trace type. Fetch from cache has a constraint with the cache type. Same for logging, db, and throw error. They all have something more. And all of a sudden, you've got something more. You've got something that really tells you more about the interactions of your systems. So we're going to talk about effect systems, how they are implemented, and their tragedies. And I will take a bit of time to do something really quick on my computer, but this will not be too far. Terribly sorry about that. So you will have the privilege of viewing my wonderful wallpaper. All right, terribly sorry for the disturbance. So we're going to talk about effect systems. And effect systems, they are quite interesting because they have a long life. From the beginning, we needed to do something more about I/O. So we have monad transformers. Monad transformers, they are a new type around values with a custom monad instance. So, for example, bollocks. Well, that's sorry, it's not very PG. So monad transformers, they have, for example, you have a value. You want to pass this value across a list of computations. You use what we call reader. It's a static environment that we pass around. So you've got a new type with reader, and with an M, which is a base monad. It's a monad on which you put this transformer, and A, which is the return value. So we stack these transformers on top one another, which means that this reader at the bottom, terribly sorry for the people at the back, we have this reader T, which has a static environment, which is an int, based on the I/O monad, which gives us I/O capabilities, and it returns a string. This computation returns a string. So that's a way of putting effects on top one another. If you want to access the underlying monad, you lift. So the idea is to use the lift method of the monad trans class to access the underlying monad. So if you have an I/O as the base monad that you have, you use lift before your put string new line function, and then as your top monad, reader doesn't need any lifting, so you can just call the ask method of the reader class, of the reader type, and then you can return the number as a string. But if you have a lot of monads stacked on top of each other, you have to lift quite a lot. So there was a shortcut developed to access directly the base I/O monad when applicable. But if you need to reach out one of the deep transformers, you still have to combine a bunch of lifts. And it really feels like going down the mines, you know. So really, it's not very economic. So that's a credible way of stacking monads in a production application. You've got an authentication environment in a reader. You've got a Redis cache with persistent settings. You've got your random number generator effects. You've got your database effects. You've got the logging effects. You've got tracing effects, and you've got I/O. Yeah, I found that in one of the code bases at work. Hi to my colleagues. So yeah, that's real stuff. And we need that kind of stuff sometimes. So to conclude, transformers, they are the historical solution for making type signature more declarative. But they have a fixed order effects because you stack your monads in a fixed order. And the same effects are always available all the time because it's one big stack. Then the monad transformer library, MTL. So here we switch from a new type to a class, a type class. So we take these transformers that we've seen previously, and we write type classes to go with them. So here, very similar. The R is the static environment that we pass along. M is the monad that we specify to have reader capabilities. And so these type classes, of course, live as constraints. So we've seen before, constraints, they live on the left side of a fat arrow in the type signature. This gives you nice things. You don't have a rigid order effect all the time. You can omit unneeded effects because instead of having one big stack of transformers, you can just specify, I'm getting only this one and that one. And what is nice is that since they have constraints, which is a native, Haskell construct, JHE can tell us about unused effects because they're just unused constraints. So that's pretty nice. So that's what it looks like. You've got your constraints on the left side of this fat arrow, and they're all on the M monad that we give back. One problem, however, is that unless GHC does heavy specialization, the same effects are going to always appear in your generated code, which means that even if you only use some of these effects, so these are all monads, so of course the bind operator is going to appear between every 2 operations in a do notation. But so you will get all the 6 binds in the generated code. And this is left onto GHC to optimize away. So GHC has to be good enough to optimize that away. We don't need to lift anymore, or at least not in the user code, but it has to appear somewhere. So in any case, lifts have to happen. It's just that we deploy them, onto the maintainers of these effects. And there are strategies to avoid to do too much tedium. But still, it means that MTL will inherit of some of transformers' bad aspects. It will, however, give you more flexibility because of the constraints. But we have had to develop GH extensions to ease the tedium of writing MTL effects. Default signatures, for example, for those who know about them, are especially used for that. Then we're going to talk about free monads. Free monads, it's a data structure that gives any kind of type a monadic structure. So it's the ability to do sequential computations. Much like semigroup can give any type a concatenable structure. So yeah, really nothing much here. The main appeal of free monad is that it's a data structure, so you can inspect it. You can take a look at it because it's just a data structure. But they're not so free because indeed you don't magically gain the ability to perform static analysis on these free monads. They're still monads, so you still have to explore branches of the program, by generating values. It's not like an applicative. So we haven't gained static analysis, magically. You still have to run your program on during 5 days, like the people in the aerospace industry have to do it to find any bugs. And there are 2 kinds of free monads, actually. There are the free monads optimized for inspection and the free monads optimized for running, for execution. And each time one of these operations is going to have to run in quadratic time and the other have a linear performance. So if you need one particular aspect of your free monad to be very efficient, you have to change the whole implementation on which you're based, which is not so great. And what is better than some free stuff? Some freer stuff. So freer monad exists. They're supposed to fix many problems of free monads, but unfortunately they remain quite exotic. But so yeah, so I'm still waiting for the freest monads to appear one day. I'm sure that would be a great paper. But yeah, and actually there's a problem with that. As I said before, it's a data structure. Your whole program becomes a data structure on top of your base Haskell program. So you have two programs to run actually. You have the program that interprets your program. And yeah, the performance is not great, I'll be honest. Sometimes it's not noticeable, but you know, yeah. I mean, I could run Lua code in my Haskell program if I wanted to have like deep nested programs living inside each other. So we've got some libraries based on that. We've got FreeSimple. FreeSimple does not allow higher order effects, which is you know, not the end of the world, but also not great. Higher order effect is just an effect that can take a computation that needs some other effects. For example, a with file operation that gives you a function, you know, to act on a file. This function could call other effects, and FreeSimple does not allow that. Polysemy, used by some people in the industry. Hello. Yes, unfortunately, it's unconditionally slow. It used to rely on a GHE plugin that actually did not work. So yeah, the benchmarks are not great. But evidently it depends, of course. If you're just running a little CLI program, you don't care much about performance. But in a setup where, you know, we have like web servers taking requests and responding, it matters. So to conclude on free monads, you've got two operations that are promoted by the structure and the research around it, run and inspect. And you have to tailor your implementation if you want, you know, any one of these two operations to be fast. Unfortunately, your program is going to be slow nonetheless. So yeah, pretty much this. As you can see, I was added, despite my request not to be added. But yes. So now, let's talk about Effectful. Effectful is a library created by Andrzej Repczak in 2021. The idea is that we needed to replace a stack of dozen transformers in our code base. And we needed excellent integration with the existing ecosystem. So we can't create, you know, the most perfect effect library, and then we have to re-implement everything. No. We have to be able to integrate with existing effects, existing third-party MTL effects, transformer stacks, that kind of stuff, exceptions. We need I/O to be seamless. So that was one of the main points of this library. We need to be reliable because it's, you know, the foundations for an application, which means that we had to were re-implemented some transformers from the transformer library, like reader, writer, state, because, for example, with transformers, you can lose some state if you have an exception happening during a state operation. So if you raise an exception and, you know, there is a bracket to catch the exception, and then you put some state, you will lose that state. It's very tricky. You don't want to debug that in production, nor do we, which is why we re-implemented that to do away with this shitty behavior. So yeah. And in the end, so we need this to be reliable foundation. How do we do that? We need low-level performance. We can't have like a normal Haskell data structure to be interpreted at runtime. We need something very low level. We need IO refs. We need some types with like hashes in the name, like small mutable array, or some stuff with the devil inside, you know. Were re-implemented some data structures like IO refs and mvar to be strict in their arguments as to avoid space leaks, because that's some of the stuff we see in production. So yeah, we need it to be performant without having, you know, 10 years of research and then people give up. And we have a constraint syntax, which means that like MTL, you can just put constraints. Unlike MTL, you just pay for what you use. We've implemented natively something like monad mask and monad unlift IO, which means that we can interact with effects that already uses those. It's very important. And it means that we've decided to make some trade-offs. for example, we don't have any real non-determinism, so we can't have multiple paths of code, suspended, executed at the same time, then resumed. Some very, nifty and neat things about resuming suspended computations, which means that we can't have coroutine as well. And so compared to some other effect systems, for example, F, which has delimited continuations, first-class support for delimited continuations, we've decided to privilege the ability of just using this library in your project, being compatible with the rest of the world, and just going on your merry way. So the ergonomics are actually fairly nice and not too alienating. We have something based on MTL here at the top with constraints. We have something based on constraints at the bottom. Some things do not appear anymore because monad base control IO, for example, monad catch, monad mask, monad throw, they are like by default in this monad that we provide to you as the effect monad. And so this is really like stuff that you don't have to specify manually, that you don't have to care about. It's all there for you. And that's actually pretty fucking nice. How do we implement effects? So I showed you how they look like, fairly standard constraints, or it can be a type-level list of effects. How do we implement them? So a static reader. So that is something. So we have this concept of static and dynamic. It's about how it is interpreted, how can it be interpreted by the effect system. So here we have our reader, which is a data structure, and we declare it to be static with no side effects on the second line. And then its static representation is, of course, its contents, because readers have an environment that they carry along. And then we evaluate this reader by calling the static representation, the data that it's inside of it. And when we need to ask for the data, it's just very simple. It's very optimized. There's like only one path. Fairly simple. There's nothing really incredible about that. We just call, the environment of this effect, and that's just it. But there could be more. So, dynamic, what does it mean? It means that we want the ability to interpret an effect differently. So here, for example, we use a feature called the GADT syntax, the generalized algebraic data type syntax, to have a reader with a member called ask and its type signature. And then when you want to ask something, you create this API with the ask function, and then you just send a sort of kind of message to your effect, say send ask. So you send a message with the ask value, and it will give you back the reader. So yes, again, nothing very magical, no type class instance, no GHX, no little GHX extension. We have to enable this nice syntax for the data reader. And but yeah, that's just a matter of syntax. So we're going to talk about quickly how to interact with existing transformers and MTL classes. So from the monadTime package, we have this class called monadTime, and it has a method called currentTime. So it even has an instance for I/O, which calls the system time, and it has even a generic overlapping instance. So that's something for the transformers and the MTL classes. So as you see, it has a monadTrans instance, and it has to lift, as I showed you earlier, manually, the transformer. A binding to such a library would be that we would create our time effect with a current time operation, say that it's dynamic, and then we would create an orphan instance of monadTime with the F monad, which is the monad of Effectful, which means that we can use natively the operations defined by monadTime, which is pretty nice, because indeed you have an instance of monadTime in your monad, provided that you have also the time effect in your context. And so I told you about dynamic effects. It's because we want to be able to either take the time from the current system, or we want to have a frozen interpretation of the time. So we can run this handler called run frozen time, which has a static timestamp, and it will always be the same kind of the same timestamp each time you request it. And it's always the same function called. It's always current time. So you can change the interpretation, the implementation really, of an effect function based on its interpreter. Something really nice is that I've developed a tool, a CI tool that does operations on the file system with symbolic links. And so I have a symbolic link effect and two interpretations. One of them acts on the file system, so it does I operation, and the other works in an in-memory map that maps, file system locations from symbolic link to a destination. Yes, Joachim? It's a very good question. So I have an IOE constraint on the frozen interpretation at the bottom. Is it truly needed? No, but I mean, it's code that I know. I think it's the interpretation. No, I think it's because yes, I think it's to please the type checker. And I talk to you about that later on because I'll check the code. But very good question. You're right. You're right to ask it. So yes, as I was saying, with a symbolic link effect, I can have a dry run option for free because I can just implement a pure or dry run implementation of this effect. So dynamic effects, you don't always need them, but they're quite useful if you need to really change the whole workings of an effect. And I want to talk about the failure mode because it's always nice when you introduce a new library and how it's great. Let's now see what happens when you mess up. So with transformers, if you somehow forget to establish your state handler in the functions that interpret your computation, you're going to get a type error, which amounts to a git diff of I needed all that and you only gave me some of that. Now please figure out what's missing. And Effectful is quite nice because it has a light overlay on top of native Haskell constructs. So it knows when it is being misused, and then it can tell you there is no handler for state int in the context. So you're trying to evaluate a computation that has state int in the type, but you haven't handled this state. You did not provide an initial state, and so it is missing. So it knows what's missing. And similarly, for things like multi-threading and unlifting, it knows when the concurrency settings are not good, and so it can tell you, with a nice exception, of course, that's one of my test suites, if you want to use the unlifted function to run F computations in multiple threads, have a look at unlift strategy conc unlift. So it is actionable advice because it gives you names that you can put on Google and then look up and then see the documentation. And so yeah, there's a straight path to action and resolution of your problem, which is pretty nice, especially for me because I'm not the creator of this library, so I don't have all the details in my head all the time, so I need to be guided to resolve my problems. So to conclude, the idea is that if you want to know more statically, or at least when you read the code, about the interactions of your program with the outside world, you should definitely pick an effect system. For application development, of course, it's primordial, especially for servers, where you have to interact with a database, a cache, a logging system, a tracing system, file storage, that kind of stuff. And a lot of people actually have been quite resisting this new trend of effect systems, especially with transformers and MTL having problems. And so they stay on the reader T IO pattern, which is that you have a reader T with all your environment, and you do IO, and that's just it. And if you want an upgrade from this, then Effectful certainly is for you, because that's one of the crowds that Effectful is trying to poach. And yeah, so we've optimized the speed of the library just for you. So yeah, I would like to thank Alexis King, Andrzej Repczak, Ningning Xie, and Xiaoyan Ren, have been, extremely useful in developing the effect ecosystem of Haskell. And you can find the sources I've used for this talk at the last slide. So yeah, that's it. Thank you very much.
Thank you so much for this great talk. Yeah, are there questions to Hécate?
Yeah, so you said there are, with free monads, you can either have linear interpretation and quadratic runtime or vice versa.
Yes.
Is the choice there, so if you want to use one or the other, you would either do something different in the type that you define, or would you use a different, so there was the, like, data free R equals pure or free.
Or you're free, yeah.
Would you use a different definition of the
Yeah,
free?
you'd have to.
Uh-huh.
You can read more about that in these two posts, Free Monads Considered Harmful by Mark Karpov, and Free Monads for Less. It's a series of blog posts by Edkmet. And so, yes, so codensity is one alternative implementation of free monads that gives you different trade-offs.
Thanks.
Any more questions?
All right, well.
I actually also have a question. So I've been following the development of effect systems in Haskell for quite some time now. And one thing that always turned me off from actually using them in production was that there is no kind of standard choice. So a effects library that's ready to use in production, that's not like we're experimenting with something academic, but rather really bulletproof and ready to use. Would you consider Effectful the standard choice if you want to switch to effect systems, or what's the status there?
I would, yes. I would definitely, because I do use it in production, in the industry, for stuff that runs in production. Flora PM, for example, runs with it. At work, we have services that run with Effectful. So yes, and also it's heavily, we run that in production. So when there is something that is messed up, we fix it as well, because it's our business that depends on it, and not the Geindex of our publications. So yes, but all the techniques are inspired by research, because evidence passing, which is the way Effectful gets the handlers across computations, is something that was published about. But the trade-offs also made it so that it was perfect for industrial users, because we don't need true non-determinism. We don't need true coroutines. We can just use the normal async, for example. So yeah, no, I would heavily recommend Effectful for production. Yeah.
Okay, thank you.
Anybody who should not use Effectful?
Well, yes. I mean, I thought about it. If you need true non-determinism, that's definitely something. If you need coroutines, all the coroutines are like really hard to implement properly. I know, like, if you need novel implementation of effect systems, like Bluefin, for example, by Tom Ellis, where the handlers are like values, and it's much more self-centered, because it needs to innovate on some core concepts. If you need such things, that don't use Effectful.
Can you go into a bit more detail when it comes to like the blocking point for coroutines and like resumable computations that you mentioned? It's just that you said it's hard to implement, and
of course. Let me point you to something.
Okay, so I go check out the exercise. Cool. Okay, that works. That works. Fair.
Christian, question?
Uh, can I ask the question first? Okay, first of all, thank you for the talk. So my question is more about the distribution of these small wrapper libraries for different kinds of effects.
Mhm.
So say you have this monad time Effectful package that wraps the already existing monad time functionality. My question is, as the library author, you might not know if the user might want to dynamically use the effect or statically. So how do you approach this? Do you make everything dynamic by default, or?
Yeah, that's a good question. So, in doubt, start with dynamic effects. It gives more freedom to the user, down the line. And should the user need dynamic effect, if you have made a static effect, you will have to re-implement it, perhaps change the API a bit. So if you start with dynamic effects, you're good. And then if you see that you have performance issues because static effects are much more performant, there is less interpretation and abstraction. So, but only should you need the extra performance, then you should switch back to static effects. So the advice is to start with dynamic effects.
Thank you.
Hi, so as Haskell programmers, we use a Haskell program that's been written before transformers that is very effectful every day, GHC. So you can apparently build large programs without effect systems, even without transformers, that operate fairly well. Do you know when we should reach for effect systems? Like, why did your company use effect systems? What was the thing like? Oh, we really need effect systems versus reader TIO.
It's a very good question. So GHC uses lots of transformers and MGL. I don't know,
they're all fixed monads, right? I thought they're all.
Yeah, you're right. I don't think they use much MTL, but they use lots of transformers. They use quite a lot of transformers.
Yeah.
With a horrible name because there's like 2 letters like JW monad, something like that. No. Lots of transformers are used in GHC. What we needed at Scrive was better interactions between monads. So for example, no state loss during exception. That's quite important. Also, the fact that, for example, the except T transformer is not a real runtime exception. It's just like control flow as data types, but then you don't get resource release and collection and garbage collection when you raise an exception. So if, for example, if you open like a port and you get an exception, or rather when you raise an except T operation, the port will not be released. The memory will not be released, that kind of stuff. So this can lead to resource exhaustion if you somehow manage to never release your resources when the accepted transformer happens. Because it's not a runtime exception, it's something implemented above normal data types. So there is no real relationship with how the runtime system handles resources.
Okay.
It's always this kind of little tricky things that for a batch compiler, for example, you can't see that much because it has a fixed length of operation. But for servers that run for like 600 days non-stop, for instance, worst case, of course you should send to production.
If it's for programs that run for a long time.
Yeah, then these little things start to accumulate, and then it's so foundational. Transformers are so foundational to every program that runs that you would want to have to debug those. It's like you wake up in your bed one day and you have to question yourself, does gravity work today? Like, wow, what? I shouldn't have to question myself on these things.
All right, thanks.
Any other questions? All right, then thanks again to Hécate. One more round of applause.